In this video, I will do some very basic examples taken from Davis and Davis textbook on chemical reaction engineering. We'll start by looking at their examples of elementary reactions and modeling their rates and the times, things like half-lives and things of that sort. So I'll start with a very simple example looking at half-lives of uranium-235. The natural abundance of uranium-235 is 0.79 atom percent. We're going to suppose that uranium-235 is not being made by any other processes and that it's just decaying to lighter elements by fission. So if we start with a sample of uranium that is enriched to 3 atom percent U-235, and that is stored underground, how long will it take the sample to reach a natural abundance level of uranium-235? Again, we're assuming that no 238 decay to 235 ever occurs. The half-life of uranium-235 is given, and that's 7.13 times 10 to the 8 years. Okay, so I think we all know that this is a first-order reaction. It's just a decay of U-235 into other things. We don't really care what exactly else it's making, strontium, cesium, etc. So all that we care about is that U-235 is being converted into something else. Okay, the radioactive decay is a first-order decay process, and we know that we can write those as concentration equals concentration initially times e to the minus kT, or in this case, the number of moles of U-235 is equal to the number of initial moles of U-235 times e to the minus kT. Okay, so we don't actually know this rate constant yet, but we are given the half-life, and the half-life is by definition the time at which half of the initial amount will be converted into something else. So then we can write the number of moles remaining after some time t as 1/2 Ni0, and that must be equal to the Ni0, the number of initial moles, times e to the minus k times the half-life. Okay, so then that allows us to go through and take logs on both sides and solve for what is the rate constant k. We get a relationship between the half-life and the rate constant that's given by this little expression here. We can then use that to solve for the rate constant, and the rate constant comes out to be 9.7 times 10 to the minus 10 years. 9.7 times 10 to the minus 10 per year, sorry. So then to calculate the time that's required to have 3 atomic percent uranium, to start from 3 atomic percent uranium and decay to natural abundance level, which is 0.79%, we then have that Ni must be equal to Ni0 times e to the minus kT. Now we know that we want Ni to be equal to 0.79, and we want Ni naught to be equal to 3. And so the ratio of those two, we're going to end up having to take the logarithm of this, take the logarithm on the right-hand side. We now know the value of k, and we'll just end up having to solve for the time. Okay, so that algebra has been done right here in this line for you. It says that the time is the log of the ratio of the initial to the final divided by the rate constant that we already solved for using the half-life. And the time that it takes then is 1.4 times 10 to the 9 years. That will be a very long time for that to decay down to natural abundance level. Now notice that our calculation is a underestimate of that time, because in reality there are processes happening in the uranium, capture of neutrons and then further decay to give you a additional source of U-235. So in reality, the decay back to natural abundance level will take even longer than this 1.4 times 10 to the 9 years, because we ignored all of those additional sources of U-235. Let's look at a more chemical example where we look at the decomposition and pressure change happening in a reactor. N2O5, the nitrogen pentoxide, decomposes into NO2 and NO3 with an elementary rate constant of 1.96 times 10 to the 14 times exponential, so that's the prefactor, times the exponential of minus 10660 Kelvin divided by temperature. Okay, so that's the activation, that number 10660 Kelvin is the activation energy divided by the gas constant. Okay, at time t equals 0, pure nitrogen pentoxide is placed in the reactor at constant temperature and constant volume with an initial pressure of 2 atmospheres. After 1 minute, we are to answer what is the total pressure in the reactor. And the temperature for this reaction is 273 Kelvin. At constant volume, we can directly use concentrations to solve this problem. So the derivative of the concentration of nitrogen pentoxide with respect to time is minus some rate constant that was given up here times N2O5 concentration. We know that we can write all of this in terms of a fractional conversion. So the amount of nitrogen pentoxide left is the initial amount of nitrogen pentoxide times 1 minus that fractional conversion. We can then write this whole ODE in terms of our fractional conversion variable x. So that is the derivative of the fractional conversion with respect to time is k times 1 minus the fractional conversion. We have an initial condition that says the fractional conversion at the initial time is equal to 0. And then we can integrate this equation. We can integrate this equation to get the log of 1 over 1 minus x is equal to k times t. Solving that for x itself gives that the fractional conversion is 1 minus the exponential e to the minus kt. So our fractional conversion as a function of time looks like this. On this axis, about the place where this kt is equal to 1, you will have converted e. You will have reached 1 over e towards your final conversion amount, and this asymptotically goes up towards reaching 1 because we have assumed that this reaction is irreversible. So in order to actually do anything numerically, we need to compute the rate constant at 273 K. We just plug in 273 K into the exponential here, and that gives us 2.16 times 10 to the minus 3 per second. So after we have reacted for 1 minute, that's 60 seconds multiplied by the 2.16 times 10 to the minus 3, and that gives us that the fractional conversion, 1 minus the exponential of the product of those two things, is 0.12. So we've got 12% conversion of our nitrogen pentoxide after 1 minute into NO2 and NO3. We can now go back and use a stoichiometric table to compute the concentrations of all species at the final stages. So we have the initial concentrations are nitrogen pentoxide is some gas constant times temperature multiplied by the initial concentration, and NO2 and NO3 aren't present in the initial mixture. After the reaction has happened, we have the amount, the fractional conversion multiplied by RT times the N2O5 initial concentration. That's the concentration of both NO2 and NO3. Of course, we've already talked about the conversion changing the initial concentration of nitrogen pentoxide. All we have to do to convert that into a pressure now is to multiply by RT. And all of these terms here have been multiplied by RT so that they represent partial pressures. The total pressure after 1 minute is going to change. It's going to be the concentration of nitrogen pentoxide times the gas constant times temperature plus a factor of 1 plus x to account for the fact that the number of moles is changing as this reaction occurs. So now we're going to write an equation for the pressure after 1 minute in terms of the pressure at the initial conditions. So the ratio of those two things should be the amount of gas after 1 minute divided by the amount of gas in the initial mixture. And all that's left from that ratio is 1 plus x. Everything else cancels away. So if we know now that the initial pressure was 2 atmospheres and the conversion was 0.12, then the final pressure after 1 minute is 2.24 atmospheres. So notice that we really didn't have to do much in the way of numerical work. In fact, the final calculation is something that you can do in your head. So it's useful to set these formulas up, cancel everything that you don't need away, and often you can avoid using a calculator entirely. So Davis and Davis, their solution looks slightly different, but the differences are really only superficial, and they get the exact same answer at the end of this problem. Let's do another example from Davis and Davis, where we look at a reversible gas phase reaction. Okay, so in this case, we have isobutene being made from 1-butene in an isomerization reaction. So if we derive the concentration of isobutene as a function of time, that's what we're supposed to do. We start out on the left. Our reactant B is 1-butene. Sorry about that, and it goes forward with a rate constant Kf to make isobutene, which can back react with a rate constant Kb to give us back the 1-butene product. Okay, so we've got B and I are the reactant and product respectively. And this reaction we're going to treat as reversible. Okay, so we have a reactor of constant temperature and initial concentrations B0 and I0 of 1-butene and isobutene respectively. So again, I'm going to take a route doing this problem that's a little bit different from the one in Davis and Davis, but the answers that I get are all the same. So the rate, the net rate, considering both forward and backward reactions, is K forward times isobutene minus K backwards times, K forward times 1-butene minus K backwards times isobutene. From the stoichiometry, we know that that rate expression must be equal to the negative of the change in concentration of the 1-butene and the positive of the change in concentration of isobutene. So we know that the equilibrium concentrations are given by the equilibrium constant, and that the equilibrium constant is the ratio of forward and backward elementary rate constants. The equilibrium, and that's the ratio of the concentration of isobutene to 1-butene. At equilibrium, that says that the forward rate and the backward rate must balance, and if we go just a little farther, we see that we can set up our stoichiometric table, and we can start with an initial concentration of 1-butene. That will go to 1-butene minus the extent of equilibrium extent of reaction variable. Then we have our isobutene. That's going to increase in concentration by the extent of reaction. So we can now solve for the extent of reaction. Everything again is going to be possible to express everything in terms of that extent of reaction variable. So we have K forward times B0 minus extent of reaction is equal to K backward times I0 plus the extent of reaction. We can solve for all of those things and put the extent of reaction variables on one side and the initial conditions on the other side, and we find after some substitution that the equilibrium extent of reaction is the initial rate of reaction, right? So the initial rate of reaction is just this quantity right here, times the inverse of the sum of the forward and backward rate constants. Okay, so that's a useful little identity that works for first order forward and backward reactions that are reversible. That the equilibrium conversion is related to the initial reaction rate and the sum of the forward and backward rate constants. Now, what we're going to do is we're going to express the rate equation in terms of our extent of reaction and our equilibrium extent of reaction. So this is the actual rate equation. This is looking at things in terms of conversion of 1-butene. So we've got the derivative of the concentration of 1-butene with respect to time with a negative sign is the rate of the reaction, the instantaneous rate of the reaction in terms of the current 1-butene and isobutene concentrations. So those can both be written in terms of these extent of reaction variables, and what we get after some simplification, again invoking our initial reaction rate, is that the derivative of the extent of reaction with respect to time is the initial reaction rate minus the extent of reaction times the sum of the forward and backward rate constants. Okay, so we can write that in terms of the equilibrium conversion by combining the initial rate of reaction, or at least writing it in terms of the equilibrium conversion and the forward and backward rate constants. So you can see that we can always replace this with a quantity that looks like xi eq times the sum of these forward and backward rate constants using the relation that we derived above. So when we do that, we find that the derivative of the extent of reaction with respect to time is a time constant that is related to the forward and backward rate constants as summed multiplied by the extent of reaction minus the equilibrium extent of reaction. So the closer that we get to equilibrium, the slower this reaction is going to go, and that's actually one of the rules that we were told before. But remember that there are counterexamples like autocatalysis where that does not hold. But anyway, this is an enlightening result because it shows that we basically have exponential decay in the deviation from equilibrium. Okay, so to put that mathematically, we have to go through and solve this equation, but what you see is that the extent of reaction is asymptotically going to be the extent of reaction at equilibrium, but it is decaying towards that with a rate that's the initial deviation from equilibrium times this exponential decay factor, e to the minus t divided by the sum of the two forward and backward rate constants. Okay, so initially the extent of reaction is 0. That's just the way we usually define things, that no reaction has happened at the initial time. So you can then write it as xi is equal to xi equilibrium times 1 minus the exponential of this decay with this time constant that's popped up in this equation. So on a dimensionless plot, you can plot the extent of reaction divided by the equilibrium extent of reaction versus time, and there's this special place along the time axis that is the time constant, or the sum of the forward and backward rate constants to the minus 1. At that point, the reaction has gone 1 over e, has 1 over e of the deviation from equilibrium left to go. So the concentration of isobutene is a function of time. Writing everything back then in terms of the actual chemical compositions is that isobutene is equal to the initial amount of isobutene plus the equilibrium extent of reaction times this declining exponential. So I think I will stop here and we'll talk about second order reactions next time.